Our goal is to extract peaks, not only the peaks, because if there are 2 points you can draw infinite ways of connecting it. So we also want the curve connecting these points. So how do we do that? So let's see a sample thing here. This is the spectrogram which we are talking about, and then what we want to extract is the smooth curve, something like this, and this is referred to as spectral envelope. Please note this term. This spectral envelope, which denotes a smooth curve connecting the formats. And if you extract spectral envelope from the spectrum, what you get, the leftovers, is called spectral details, which will be something like this. So if you denote this spectrum as log x of k is a spectrum. Since we are in the log domain, see the dv here, that's where we got log x of k. And if you denote the spectrum as log x of k, then the spectral envelope could be denoted as log h of k, and spectral details could be denoted as log e of k. So our goal is to separate spectral envelope and spectral details from the spectrum. Our goal is to extract this spectral envelope from this. That is, given log x of k, obtain log h of k and log e of k such that h of k and e of k, log h of k and log e of k sum together to form log x of k. So our goal is to represent log x of k into a set of 2 components. If you sum them up, you should get back the log x of k, and these 2 components should be such that one of the components should be representing the spectral envelope and the another component should be representing the rest of the details. So that's our goal. So how to achieve this separation? So let's play a mathematical trick to achieve this separation. Okay, so what's the trick is about? So the trick is to take the FFT of the spectrum. So please note that this is already FFT of the speech signal, and then we are talking about the taking FFT of the spectrum itself. So that's a trick. So in a moment I'll explain how we can do that. So if you take an FFT of the spectrum, then it is referred to as inverse Fourier transform, inverse fast Fourier transform. That's where it is denoted by IFFT. So typically if you have a spectrum and then if you take an IFFT, it will give you back the speech signal in time domain. But here we are talking about the spectrum which is already there in the log domain. That means we have done some operation. So the moment we have gone to log domain, then if you take IFFT of this log spectrum, it would give you this signal back in terms of pseudo frequency axis. It is no more in time domain, but what you get when you take IFFT of this log spectrum is a representation in pseudo frequency axis. So let's say this is a pseudo frequency axis, and then this is a low frequency region of the pseudo frequency axis, and this is a high frequency region of the pseudo frequency axis. Okay, so let's do a bottom-up approach of how to achieve a separation of spectral envelope and spectral details from this spectrum. So let's see that, we have already separated out. That's where I'm saying it's a bottom-up approach. So we'll go from assuming that we have got the separation, and then we'll see how to derive from this point. So now our goal or our task is to take IFFT of this spectral envelope. If you see the spectral envelope, for a split of second, forget that this is a frequency axis. Treat this as a time axis, and this is a 1 second window. So if you see carefully here, you can approximate or like grossly say that there are 4 sine waves, or this is a sine wave. You can see that this is a sine wave with 4 cycles per second. 1, 2, 3, 4. So that's where I'm saying it's 4 cycles. I'm saying this is a purely in tissue analysis, so just bear with me and then treat this as a sine wave with 4 cycles per second. So what do we mean, or what is our knowledge if you have a sine wave with 4 cycles per second? So we should get a peak at 4 Hz in frequency axis when you take Fourier transform of this sine wave, correct? So that means I should get a peak at 4 Hz, which is in the low frequency region. So let's say I've got a peak here, which is a low frequency region, which denotes the number of cycles that it has in this signal. Okay, so because this is a very slow varying, we assume that there are 4 sine waves, 4 cycles of the sine wave. That's where we said 4 cycles per second. That would give us 4 Hz. That would give us a peak at 4 Hz, which is denoted in the low frequency region with this peak. Let's move to this signal here. Let's say we want to take IFFT of this signal. If you see here, this is a fluctuating signal or highly varying signal. Let's say we want to say that there are about 100 cycles per second here. So this also, let's treat this as sine wave, and then there are about 100 cycles per second here. So this is because this is a highly varying or fluctuating signal, we said 100 cycles. So what do we mean by that? So when you take a FFT of a sine wave with 100 cycles per second, you would get a peak at 100 Hz in the frequency axis. So this 100 Hz is in the high frequency region, so that means you should get a peak somewhere here, correct? Okay, so we're done with the IFFT of these two. This is a slow varying signal, that's where you get a peak at a low frequency region. This is a high varying signal, you get a peak at a high frequency region. So now let's get back and then let's denote that this is log h of k, this is log e of k, and then this is log x of k, which is represented using this way, log x of h of k plus log e of k. Okay, so now we want to take IFFT of this signal. So if you take IFFT of this signal, or let's say apply IFFT on this equation, so you would get back an signal x of k like this, okay, which is denoted as h of k plus e of k, correct? So that means to obtain x of k, you need to sum the h of k, which is here, small h of k, please note that, and then small e of k. So if you sum these two, you would get back x of k. So that's what you would get here. So when you take IFFT of this, you would simply get the summation of h of k and e of k, correct? But in practice, you know, all you have is access to this spectrum, and then then you can take IFFT of this. That would give you something like this. Okay, so it would directly give you an x of k. But from the analysis what we have seen earlier, we know that low frequency region corresponds to the spectral envelope and the high frequency region corresponds to the spectral details. So that's a clue here. So to understand that low frequency region correspond to the spectral envelope, we have gone through the bottom-up analysis. So if you know x of k, what you can do to get h of k is to simply use or filter the low frequency components, low frequency region. That means use only the components or the coefficients present in the low frequency region to get h of k. So this is a crucial point here. So you get x of k, and you know that the interpretation of x of k is such that because it's a pseudo frequency axis, the lower coefficients or the coefficients present in the low frequency region correspond to the spectral envelope, and the coefficients present in the high frequency region corresponds to spectral details. So if you have a signal, so typically this x of k is referred to as spectrum, sorry, cepstrum. So you get the cepstrum, and you can obtain h of k by considering the low frequency region of x of k. So h of k represent the spectral envelope and is widely used as feature for speech recognition. So this is the in-tissue analysis of how to get the spectral envelope we are talking about. So you take the log spectrum and then take the IFFT out of it, and this is the pseudo frequency axis, and then you get the x of k. Once you get the x of k, the interpretation is that low frequency region of x of k represent the spectral envelope and the high frequency region represents the spectral details. So so you can obtain the spectral envelope by taking the low frequency region here. Again, I'm emphasizing that x of k is the cepstrum, and the low frequency region of the cepstrum is the feature which we want because it represents the spectral envelope. So this is a mathematical analysis of it. So if x of k is a spectrum, it consists of two components, spectral envelope and spectral details. If you take the magnitude of it, this is the equation, and then take log on both sides, this is the equation. The moment you take log, it will get a summation here. Then take IFFT, inverse FFT, you get this equation. Once you get this signal, take the low frequency components, that would give you h of k. So the cepstral analysis can be applied to any spectrum to get the spectral envelope. So let's move into our next topic, Mel frequency analysis. So let's stop a bit and then review what we did. We captured spectral envelope from the spectrum. That means we got a curve